Good day students. So in our today's session we are going to see about RISC architecture. So in our previous session we have seen about CISC architecture. Under CISC architecture we have seen about VAX architecture and Pentium Pro architecture. So today we are going to see about RISC architecture. RISC stands for Reduced Instruction Sets Computers. So here our instruction sets are very much reduced, but the complexity is also increased. Now let us see about the general features of RISC architecture. Coming to the instructions, so the instructions are of standard fixed instruction format. All the instructions will execute in a single cycle. So single cycle executions of instructions are available. All are register to register access only, whereas memory access will take place only for load and store operations. Remaining all are register to register operations. Our instructions, the total number of instructions are very small, and also the instruction format is also very small. So these are the general features about the instructions. Whereas registers there are a large number of general purpose registers. Addressing modes, a very small number of addressing modes. So these are the general features of our RISC architecture. RISC architecture is categorized into three types: PowerPC architecture, SPARC architecture, and Cray T3E architecture. So today, in today's class, we are going to see about PowerPC architecture. Power stands for Performance Optimization with Enhanced RISC. Performance Optimization with Enhanced RISC. This PowerPC architecture is introduced by IBM in 1990 at a cost of rupees 6,000. Then later on, IBM, Apple and Motorola, so all these three companies formed an alliance to develop PowerPC in the year 1991, whereas the first product under PowerPC was delivered in the year 1993. So the recent implementations of PowerPC architecture are PowerPC 601, 603, 604. So this is a general introduction about PowerPC architecture. So it is developed by IBM. Next feature, memory. So let us see about the first hardware feature, memory. Since RISC architecture comes under complex computers. So our memory is also segregated into two types, physical memory and logical memory. So physical memory is categorized into half word, word, double word and quad word. 2 consecutive bytes form a half word, 4 consecutive bytes form a word, 8 consecutive bytes form a double word and 16 consecutive bytes form a quad word. Coming to logical memory, so logical memory is segregated into segments. So the segments are of fixed length. So the length of each segment is 256 MB megabytes. Again, segments are segregated into pages. Pages is also of fixed length. So the length of each page is 4 KB. The total size of our logical, that is virtual memory, virtual space is 2^64 bytes. So this is the total space of our virtual memory, that is the logical memory. So while execution, these virtual address has to be converted to physical address. So this conversion is handled by our memory management unit of our operating system. So that's all about memory. Now let us see the next hardware feature, registers. Registers. So registers are of 64 bits. All registers are 64 bits. There are 32 general purpose registers. So the registers are general purpose register GPR0 to GPR31. So always the register GPR0 will contain the value 0. So the value 0 is always stored inside the 0th register, that is GPR0. Floating point unit. So under floating point unit, there are 32 floating point registers. All registers are of 64 bits and it also contains status and control registers. Then condition code registers. Condition code registers are also there, CC registers. So this is of 32 bit. So our condition code registers will reflect the result of certain operations and can be used as a mechanism for testing and branching. So it will store the result of our testing and branching. Then link registers, LR register. Count registers, CR registers. So these both are used for branch instructions. Then we are having a MSR register, that is machine status register. Machine status register. So this machine status register will hold the current status of our machines. So that's all about the registers. So, we are having 32 general purpose register, then under floating point unit 32 floating point register, status and control register, then we are having a condition code register of 32 bit, link register, count register and MSR register. Next, hardware feature, instruction formats. So, in our PowerPC architecture, we are having 7 instruction formats. All instruction formats are 32 bits long. First 6 bits identify the opcode, that is the operation. Some instruction also have an additional extended opcode also. This is not supported by all instructions, only some instructions will have the extended opcode. Complexity of instruction set is higher than our Spark architecture. So, we will be seeing about Spark architecture in our next class. So, the instruction format, the complexity of the instruction format of PowerPC architecture is very much higher than Spark architecture. Since as we have seen before, all the instruction formats are fixed length. On because of fixed length instruction format, the decoding of instruction is very much faster and simple than VAX and x86 architecture. So, VAX and x86 architecture comes under CISC family, CISC family. So, our in our RISC architecture and under PowerPC, all the instruction formats are fixed length. So, the decoding is nothing but the conversion of our higher level language to the machine level language. That process is called as decoding. That decoding process will be very much faster and simple than VAX and x86 architecture. So, that is all about instruction formats. Next hardware feature is addressing mode. So, we are having only a smaller number of addressing modes in our PowerPC architecture. So, the addressing modes available are immediate mode. So, in immediate mode, the value of the operands is given in the instruction itself. Then register direct mode, register indirect mode, register indirect with indexed mode, register indirect with immediate indexed mode, absolute addressing mode, relative addressing mode, link register addressing mode and count register addressing mode. So, these are the addressing modes available in PowerPC architecture. Now, let us see how to calculate the target address under each addressing mode. So, the target address for immediate addressing mode is specified in the instruction itself. So, the target address is present in the instruction itself because the value of the operands is present in the instruction itself. In register direct mode, the target address will be stored inside the register, that is the value of the operands will be stored inside the register. Then in register indirect mode also the target address is calculated by obtaining the address that is present inside the register. in that address we will have our destination value. So the register will holds the address, we have to fetch that address and go to the address to obtain our destined value. Then under register indirect with indexed mode, the target address is calculated by subtracting the value that is stored inside the register minus 1 plus subtracting the value that is stored inside the register with minus 2 and adding both register minus 1 plus register minus 2. Then the target address for register indirect with immediate indexed mode is calculated by target address is equal to the value stored inside the register plus displacement. So the displacement will be 16 bits and signed. Then for absolute address, target address is calculated by target address. Absolute means nothing but the target address specified in the instruction is our actual address. Then for relative mode, target address is equal to current instruction address plus displacement. So displacement of 25 bits and signed. Current instruction address plus displacement. The target address for link register is equal to the value that is stored inside the link register, and for count register, target address is equal to the value that is stored inside the count register. So that's all about the addressing modes available in PowerPC architecture. Next hardware feature is instruction set. So coming to the instruction set, we are having at most 200 machine instructions. So all these machine instructions are very much complex in our RISC architecture. For example, how I will say the complexity of the instructions will be. So usually we will be doing the addition, multiplication and all the architectures that we have seen before using only 2 operands. Whereas in RISC architecture we will be doing any operation like multiplication or addition operations with 3 operands and more than 3 operands. So there lies the complexity. Then the load and store instructions may automatically update the index register to obtain just the computed target address. In order to obtain the target address, so the load and store instructions may automatically update their value. So that's all about the complexity. So since our instructions are very much complex, the execution will be pipelined. So pipelined execution is possible. Pipelined execution is nothing but when one instruction is executing, we will fetch the next instruction and decode it to make it ready for the execution. So that is called as pipelined execution. The pipelined execution of our PowerPC architecture is more sophisticated than Spark architecture. So that efficiency, that sophisticated, since the pipelined execution is more sophisticated than Spark architecture, the efficiency is very much improved. So how this sophisticatedness is given to our PowerPC architecture means by utilizing branch prediction method. So while executing itself, we will be predicting where a branch will occur, and accordingly that branch instruction will be pipelined. So since we are using branch prediction method, the efficiency of pipelined execution is very much improved in our PowerPC architecture. So that's all about the instruction set. So finally, the last hardware feature is input and output, I/O. So for performing I/O, we are using two different modes. One mode is direct store segment, and another mode is normal virtual memory access. So under direct store segments, the segments in virtual address space are mapped onto an external address space, typically an I/O bus. Whereas in normal virtual memory access, a reference to an address that is not in a direct store segment is normally present in a virtual memory access. So I/O is performed using virtual memory management hardware and software. Okay. So normal virtual memory access will takes place to the address that is not present in direct store segment. If the address is not present in a direct store segment, then I/O is performed by using virtual memory, that is normal virtual memory access. If the address is present in our physical memory, if it resides in our physical memory, then we go for direct store segments. So we have seen in our previous architecture, in our memory itself, we are having certain registers to perform I/O operations, that is a certain portion of our memory is allocated for performing I/O operation. That memory is called as I/O space. So under I/O space, there are some registers that are involved in doing input and output operations. So that kind of memory, that kind of input and output operation is called as direct store segment. If the address is not stored in physical memory, if it resides in virtual memory, then the I/O is performed using normal virtual memory access. So that's all about I/O operations. So we have seen all the hardware features under PowerPC architecture. Hope you understand it. So in our next session, we will be seeing about the next architecture under RISC, that is Spark architecture. Spark architecture is introduced by Sun Microsystems. So let us see in detail in our next session. Thank you.